Module 7, Blockchain Platforms. Lecture 3, Overview of the Ethereum Platform. In this lecture, we will cover the following topics: support, technology, networks, dApps, scaling. This lecture is part of Module 7, Blockchain Platforms. With this lecture, you're going to learn how to indicate key objectives of Ethereum, recognize the characteristics of the Ethereum blockchain platform, explain blockchain technology ecosystem, underlying basic algorithms and essentials of trust in Ethereum, describe the Ethereum's approach to scaling and interoperability. The minimum requirements for this lecture are: basic understanding of blockchains. Ethereum is the #1 platform for decentralized applications. It consists of public Ethereum networks and permissionless access. The cryptocurrency used is called Ether, or ETH for short. It is effectively evolving towards the multi-layer architecture. It has a large and vibrant community of developers and users. It covers key application domains: DeFi, NFT, DAO, and gaming. Ecosystem. The Ethereum network has become sufficiently decentralized that no one party controls the network. Governance is off-chain. A social discussion between stakeholders decides how and when upgrades or changes are made on the network. Stakeholders include ETH token holders, application users, application and tooling developers, node operators, validators, protocol developers, and Ethereum Improvement Proposal (EIP) authors. The nature of such a community-driven project means that the network is decentralized, which adds to implementation security. Because no one controls the Ethereum network, no one person or party can make changes to the protocol. The community must agree to specific protocol changes, which can be slow. The Ethereum platform is permissionless, and all source code is open-sourced. It is important to note that most decentralized applications, dApps, are also open-sourced, but some might not be. Technology. Ethereum has chosen a modular network architecture approach, where blockchain functions, execution, settlement, consensus, data availability, are outsourced across specialized chains. Ethereum scaling is achieved by encouraging rollup use, where transactions can be processed in several orders of magnitudes faster than on the main chain. Of course, transactions can still be processed on the mainnet but with higher fees and confirmation times. The functions and where they happen: Layer 1, L1 or Layer 2, L2, on Ethereum. Execution, L2, rollups, L1, mainnet, the environment where computations required to update the chain state happen, transactions. All transactions are processed on L1, mainnet or L2, rollups, encouraged. In the case of L2, rollups, usually a centralized server called sequencer processes transactions off Ethereum L1, mainnet, which considerably lowers fees. Settlement, L1, mainnet, the process of guaranteeing that the committed transactions, batch, are valid and irreversible. For this, the chain is used by execution layers to verify proofs, resolve fraud disputes, and bridge between other execution layers. Consensus, L1, mainnet, L2, rollups, the mechanism by which nodes agree on the order and validity of transactions and, thus, the content of the next block. Data availability, L1, mainnet shards, the guarantee that transaction data is available to download. Ethereum is a distributed state machine where the state is a data structure that holds information of all accounts and a machine state. It's important to differentiate between a UTXO-modeled blockchain, Bitcoin, and an account-modeled one. In the UTXO model, the state is stored directly in transactions, while in the account model, transactions represent state transition instructions. So conceptually, blockchain data in Ethereum can be separated into chain data, the list of blocks forming the chain, and state data, the result of each transaction's state transition. Chain data is permanent, for example, transactions. Once fully confirmed, they cannot be altered. On the other hand, state data is ephemeral, for example, account balances. An account's balance is altered whenever a value transaction uses that account's address. The Ethereum Virtual Machine, EVM, defines the rules for machine state changes. Data required for smart contracts is referred to as the machine state. The EVM is the computing environment of Ethereum that takes care of executing instructions. Every instruction that gets executed costs a certain amount of gas. That is why interacting with smart contracts, example, sending tokens, is more costly than sending only ETH, native coin. The Ethereum network is comprised of validator nodes that run copies of the EVM. All copies are kept in sync via the consensus mechanism. Nodes have to run two pieces of software, the execution client and the consensus client. The execution client listens for new transactions broadcasted in the network and then executes them, EVM. It also holds the latest state and database of all current Ethereum data. The consensus client implements the POS consensus algorithm, which enables the network to achieve agreement based on validated data from the execution client. Ethereum uses a proof-of-stake consensus mechanism for nodes to agree on the state of the blockchain. The transition to proof-of-stake from proof-of-work took place in September 2022. The transition replaced miners with validators, resulting in a 99% reduction in energy consumption for the network. The introduction of POS also paved the way for other upgrades, such as sharding called danksharding. Overview of the mechanism. To participate as a validator, users must stake 32 ETH and run three separate pieces of software: execution client, consensus client, validator client. Every 12 seconds slot, a random validator is chosen to become a block producer. Block producers must choose transactions from the mempool, a pool of user-submitted transactions, or elsewhere and construct a block. The block must then be broadcasted on the network for other validators to see. Also, in every slot, a randomly selected committee of validators must vote on the validity of the newly proposed block. The next measures are taken to prevent validator attacks on the network, be that personal gain or sabotage. Validators miss out on rewards if they fail to participate when chosen as block producers. A validator's existing stake can be destroyed if they behave dishonestly. Proposing multiple blocks in a single slot, submitting contradictory attestations/votes. Block production time is divided into slots, 12 seconds, and epochs, 32 slots. In every slot, a random validator is selected as a block producer, and a random committee of validators votes on the proposed block to determine its validity. To prevent oversized blocks, the size is bounded by gas units used. Each block has a target size of 15 million gas, but the size of the blocks may increase or decrease depending on network demands. The block size limit is 30 million gas. Bounding block size is important because nodes need greater computing power and space to process larger blocks in time for the next slot. Transaction finality is achieved when the transaction is part of a block that can't be changed without a significant amount of ETH getting burned, more than 1/3 of the entire staked ETH. On Ethereum, this is managed by using checkpoints. Checkpoints are the first blocks in every epoch. Validators vote for pairs of checkpoints, and when a pair represents 2/3 or more of the total staked ETH, the checkpoints are upgraded. The more recent one becomes justified, and the previous one becomes finalized. Because a 2/3 majority is needed to achieve finality, someone with 1/3 of the total stake could prevent the network from achieving finality. For that reason, if finality is not achieved for more than 4 epochs, the network slowly burns the stake of those voting against the majority. Ethereum has 2 account types: externally owned accounts, EOAs, and contract accounts. As the name indicates, EOAs are accounts owned by something external to the blockchain users. EOAs are created and controlled by key pairs, private key and public key. It also costs nothing to create an EOA. These accounts cannot store code. They can only send messages, transactions. Contract accounts belong to smart contracts deployed on the network. They are managed by code and can execute many functions when called by EOAs. They cannot execute code without receiving a call from an EOA. EOAs or other contract accounts can create them. Creating one always comes with a cost. The larger the code of the contract, the higher the fee will be because the code needs to be stored. In the Ethereum ecosystem, there are many ongoing discussions and development around account abstraction. Ethereum account abstraction aims to reduce from 2 account types to 1, a contract account. Some rollups have already implemented account abstraction: Starknet, zkSync. The single account type will have the functionality to transact tokens and execute code as smart contracts do, allowing unique wallet designs that provide new important features. Some features: account social recovery in case of lost private keys. Batch transactions: an array of transactions gets processed as one transaction. Interact with dApps without owning ETH, pay with other tokens. Wallet upgradability: change keys, upgrade code. It is already possible to achieve some of these features using smart contract wallets, but with added costs. The reason is that an EOA needs to trigger a transaction on smart contracts, adding additional cost and complexity, paying for an extra transaction and managing balances in 2 accounts. Ethereum is transitioning from a monolithic approach to a modular approach. Monolithic blockchains handle execution, settlement, consensus, and data availability. The effects on storage of such an approach are: expensive data storage, because every node had to store all the data. It is not feasible for all nodes to continue running because of a constantly growing chain that requires nodes to upgrade storage capacity. With the modular approach, where certain functions are being outsourced outside of Layer 1, the scaling will be significantly increased, allowing for cheaper transactions on Layer 2, rollups. Rollups must publish all transaction data and proofs on L1. The cost of publishing is distributed among rollup users, but it still represents the majority of transaction fees. Because data storage is expensive, new upgrades are planned for 2023/2024, introducing a cheaper data type for rollups and data sharding. These upgrades will significantly lower data storage costs for L2S and, consequently, will lower user transaction fees. Transaction fees are calculated by multiplying the gas limit by the sum of the base fee and the priority fee. Gas is a unit representing the computational effort required for a specific operation. Consumption of gas units varies depending on the complexity of a transaction. The more complex the transaction is, the more operations are needed, so more gas units will be consumed. The maximum amount of gas a user is willing to spend on a transaction is the gas limit. If the specified limit is higher than the actual consumed amount, the rest is returned to the user, but if it's lower, the transaction will fail. The price of gas units is denominated in ETH. The base price is the minimum price per gas unit for the transaction to be included in the next block. The price depends on block space demand. Priority price is used to add a tip for validators to include a transaction to the next block. Transaction fee equals gas limit bullet operator, base price plus priority price. The base fee, gas limit * base price, is burned while the priority fee, gas limit * priority price, goes to the validator that includes the transaction in a block. Burning the base fee presents a unique situation in Ethereum's network because, in times of high block space demand, the amount of ETH burned surpasses the amount of newly created ETH, validator rewards. This means that, at times, the ETH supply can become deflationary. It's important to note that Ethereum does not support native/colored tokens as some other blockchains do. Every non-native token on the Ethereum network is a smart contract. Hence, the price for transferring them is higher, more operations. Oracles are data sources that connect Ethereum smart contracts to off-chain resources. Input oracles enable the execution of smart contracts based on real-world data. Output oracles allow smart contracts to send commands to off-chain systems. Cross-chain oracles read and write information between different blockchains. Compute-enabled oracles allow blockchains to use off-chain computations. Oracles provide trust. Ethereum has no native oracles. Smart contract usage leads to an ecosystem of oracle services, Chainlink, Witnet. On Ethereum, there is no natively enabled data privacy. All data written on-chain can be seen by everyone. To achieve data privacy, one must encrypt all data before writing it on-chain. To achieve account privacy, keep your personal information private, one must follow good practices. Running your node instead of using third-party providers. Running your own node means you have a complete copy of the network. You also achieve censorship resistance and improve the decentralization of the network. Changing addresses regularly. Use of privacy dApps. With the use of smart contracts, many privacy-oriented dApps have been created. For example, Tornado Cash allows users to transfer funds to other addresses without leaving a trace back to the initial source/address. However, regulators are concerned about the money laundering ability that such dApps allow. Use privacy-preserving Layer 2 rollups. For example, the Aztec network rollup is built to be fully privacy-preserving. Networks. For production-ready dApp deployment, both L1 ETH mainnet and L2 rollup mainnets can be used. It is important to note that rollups are extensions of Ethereum and not standalone blockchains. Using rollups considerably scales transaction throughput and lowers costs. Specific rollups can add other advantages like security and interoperability. Some may also allow other tokens to be used for transaction fees, for example, using stablecoins like USDC instead of ETH. Before deploying on the mainnet, developers can use testnets for L1 and L2. Local virtual environments are also available for testing. Because client implementations are open-sourced, they can be reused and tweaked for running private networks or other public networks. Many projects use EVM because of this, with added perks, different consensus clients, block parameter changes, etc. The Ethereum network is a public network that allows anyone to participate. The level of decentralization and security is high. We should look at decentralization from a higher perspective and not only at the number of nodes. There is a high number of developers and community members worldwide, which is good for the longevity and security of the network. The native coin ETH is highly distributed, which prevents the possibility of price manipulation and adds to consensus security, harder to achieve a majority stake. There are multiple node client implementations, good for security if there is a bug in a client implementation. We must remember that because of the POS consensus mechanism, stakes get /burned if validators do not participate or if they vote maliciously. Multiple implementations with equal participation mitigate the risk of a massive slashing event and allow validators to switch to another implementation in case of a bug. Having a high number of validator nodes further improves decentralization and lowers the risk of collusion. Ethereum's ecosystem is overly reliant on infrastructure providers. Even though the blockchain will always stay operational, using third-party providers for wallet user interfaces, web pages, nodes, etc., presents a risk for users. Ethereum Improvement Proposals (EIPs) are standards specifying potential upgrades for Ethereum's network. Upgrades can be new features or processes created and proposed by anyone in the community. EIP process. After proposing an EIP, it must be presented to all core developer teams, posted on a forum and call. If the proposal is accepted, technical changes might be requested. Once all changes have been made, the proposal must be presented again. Assuming the EIP is approved, tested, and implemented, it gets scheduled as part of a network upgrade. The network is upgraded to include approved EIPs. The network upgrade procedure considers all stakeholder opinions, which means that no one has full control, which comes with a very long time for EIP deployment, multiple calls, reiterations, testing. Disagreements are handled with discussions. If there is no resolution, a chain split is possible. dApps. The backend code, smart contracts, runs on a decentralized network. Once deployed, smart contract code can't be taken down. Has no downtime. Has resistance to censorship. Has complete data integrity. Has trustless computation / verifiable behavior. Front-end code, user and machine interfaces, usually runs on centralized servers, AWS, but can be run on decentralized alternatives like IPFS. dApps allow for persistent, uncensorable, and secure applications on Ethereum. dApps on the Ethereum network also have built-in payments in the form of tokens. Smart contract supported languages are Solidity, Viper, YUL plus, low-level languages. Rollups can support other languages. For example, Starknet uses Cairo. dApps are a vibrant community with many projects. Decentralized finance, DeFi. Public funding. Collectibles, NFTs. Decentralized identity. Decentralized social networks. Decentralized autonomous organizations, DAOs. Scaling. Ethereum's scaling approach is to use L2 rollups to offload transactions from L1. Rollups are a layer 2 scaling solution divided into optimistic rollups, OP rollups, and rollups that use zero-knowledge proof technology, ZK rollups. Zero-knowledge proofs are cryptographic methods that prove a certain assertion is correct without providing any other information. Rollups must publish data, bundles of processed transactions, on Layer 1. Because writing data on Layer 1 is costly, publishing represents the majority cost of transaction fees on rollups. Ethereum's solution is to allow cheaper storage in L1 for rollups, further lowering rollup fees. Cheaper rollup storage is achieved by implementing a cheaper data type for storing rollup data and creating data shards. Sharding the data allows for even cheaper storage because nodes no longer need to store all the rollup data. True interoperability allows different Layer 1 blockchains to exchange data and funds without intermediaries. Interoperability between different L1s is usually not natively supported, but it is achievable by using smart contracts. Bridges are smart contracts used to transfer tokens from chain A to chain B. Firstly, the tokens need to be locked on chain A and then minted on chain B, representations of the actual token. Using such implementations raises security concerns. Who verifies the system? Is it corruptible? Many bridges have already been exploited, with hundreds of millions of funds stolen. To maximize security, a system must be verified completely by one validator set, for example, verifying everything using Ethereum's validator set. This is achievable by using Layer 2 rollups. There is high interoperability between L1 and L2, but even the introduction of rollups brings new concerns in the case of rollup-to-rollup interoperability. L2 to L2 solutions, bridges, utilize their own set of external verifiers, meaning that Ethereum's validator set no longer secures your funds. The most secure way is going through L1, L2.A to L1 and then L1 to L2.B, which is expensive. Thank you for listening to this lecture.